So the ideal gas law. We've talked about simple gas laws. Those are relationships just between two variables, pressure and volume, temperature and volume, etc. If we combine those relationships, we come up with an expression that the volume is proportional to the number of moles times the temperature divided by the pressure. And to make a proportionality into an equality, you put a constant in there. So then we say that the volume is equal to N times the constant R, T over P, or rearranged into its more familiar form, PV equals nRT. This is known as the ideal gas law. It's an important gas law. The R in this equation is called the ideal gas constant, and it can be expressed in different units depending on what units are used for the temperature and the pressure. So using atmosphere for pressure and liters for volume, we get R is equal to 0.08206 liters times atmospheres divided by mole times Kelvin. And yeah, those are really messy units, but those are the units of the other variables in the equation, and so then all the units cancel out. There's a relationship between the ideal gas law and the individual simple gas laws that we've looked at. In each of these cases, we hold two of the variables constant and allow the other two to vary. So here volume and pressure can vary, but the amount of gas and the temperature are the same. Excuse me. So I'd like to show you some, well, they're kind of tricks, I guess, that you can do with the ideal gas law. Let's choose something bigger. That's better. So we can write the ideal gas law, PV equals nRT. And if I divide that by itself, if I divide PV by PV and I divide nRT by nRT, is that still an equality? I did the same thing to both sides, right? So I've got green PV equals nRT and blue PV equals nRT, and I could put numbers on these. I could say this is P1, V1, N1, and T1, and I could call these P, V, and N, and T2. Because we can look at just this bottom part, and P2, V2 is equal to N2, R, T2. It sounds like I'm talking in some code. So dividing this side by this term and the other side by the other term, I'm still dividing by something that's equal, it's still valid. Why would I want to do this? From this, we can make any of the equations that we need, any of those three simple gas laws, and there's a couple other ones that we haven't talked about, and they're all hiding right here. So obviously R doesn't change, right? That's a constant. So I'm going to erase R. R divided by R is 1, it cancels out. So to make any of the other gas laws, I'm just going to cross out the things that are not changing. So let's just say that we had something where the pressure and the volume were changing, but N and T are constant. And so we need an equation for that. I'm going to look at this equation and I'm going to say, well, N1 over N2 is the same because the moles isn't changing. T1 over T2 is the same. They're not changing. Well, what does the right side equal then? I canceled everything out. Is it 0? What's anything divided by itself? 1. So if I have N over N and T over T, that is equal to 1. Okay? So I could rewrite that. I'm going to erase these because I want to use this again. So I can erase that. I can rewrite this over here. I had P1 V1 over P2 V2 was equal to 1. I can cross multiply, however you want to think about it, rearrange this, and get P1 V1 equals P2 V2. And that's what we learned as Boyle's law, right? Let's say that, N V, and T are changing, and only P is constant. That's not one we've looked at. That has 3 things changing instead of 2. But we could do it anyway. So the P being constant tells me that P1 and P2 are equal to each other. So they cancel out. Right? So then I look at what's left. Well, I'm just going to do this over here. V1 over V2 equals N1 T1 over N2 times T2. That could be rearranged into a prettier form, but you can also just use it like that. You can use this equation as is and just rearrange it to solve for whatever you need. This is sometimes shown this way: N2 T2 over V2 is equal to N1 T1 over V1, and that is sometimes called the combined gas law. So what I'm trying to show you here is if you learn the ideal gas law, you can divide it by itself, and you can quite simply derive all the other equations that you need. Any questions? So let's do an example here. This is with the ideal gas law. An 8.5 liter tire contains 0.552 moles of gas at a temperature of 305 Kelvin. What is the pressure in atmospheres and PSI of the gas in the tire? So let's pretend that it's Monday morning and we're not really awake yet. Oh wait, that's true. We're just going to go through this. We don't realize that we're doing an ideal gas law problem. We're just, on track with doing the other things we were doing. So we're going to make a table and we're going to collect all the numbers. So the first number I come to is 8.05 liters. And I say, well, I think that's a volume, right? Because of the unit. So I'm going to call that column V. And I'm going to call this row number 1. And it says it contains this much gas, 0.552 moles. Well, what's the variable for moles? N, number of moles. And then at a temperature of 305 Kelvin, that's the temperature. The unit there is Kelvin, which is the one we need, so we don't have to convert anything. And what about this second row? There's no second row, because nothing is changing here. This isn't a simple gas law problem where you've got this thing changing and that thing changing. We're just saying this is it. This is what it is. What's the missing variable? So I don't need the second row because there's no second set of numbers. Making the table was not a waste of time though, because what have I done? I've labeled all my information. I see that nothing's changing. That tells me I need the ideal gas law. PV equals nRT, sometimes affectionately known as PivNert, an attempt to pronounce it without any vowels. So what is missing? What am I supposed to find? The pressure. I'm supposed to find the pressure. There's pressure. So I want to rearrange the equation so I can get P by itself. P equals what? So I'm going to divide both sides by V. The volumes cancel out. And so I get the pressure is equal to nRT over V. So I have V, N, and T. I don't have R. We should memorize R because it's going to come up a lot. R is equal to 0.08206 liters times atmospheres divided by moles times Kelvin. These units tell me what the units on all my other things have to be. So I'm going to start plugging in numbers, and always, always, always include the units. So N is 0.552 moles. N equals 5.552 MOL. R, 0.08206 liter atmospheres per mole Kelvin. Temperature, 305 Kelvin. And then in the denominator, I've got the volume, 8.05 liters. Before I do a bunch of math, I want to make sure that my units are okay. So in the numerator here, I've got moles, and here I've got a fraction where I'm dividing by moles. The moles cancel out. And the kelvins cancel out as well. And now I've gotten rid of the denominator of that fraction, so I've just got liters times atmospheres here, and so the liters will cancel out. Yes? Thank you. It was 8.5 liters. Yep, transposed digits. I don't do that very often, but I did it today. Thank you. 50 and 50. That's going to make a difference. There are many reasons why I want you to write down at least this. Okay? I know, you're like, oh, I'll just punch it through on my calculator. Well, that's great, but then if you made a mistake, you can't learn from your mistake. And you also can't go back and remind yourself what you did. So always write this down. So now we get out the calculator, and I'm going to multiply by all those things on the top. And divide by 8.50. And if I look at all these numbers, most of them have 3 significant figures. The ideal gas constant has 4. So my answer should have 3 sig figs. 1.62, I'll write down 2 more digits. That's liters, and that will round to 1.63 liters. No, it's not liters, is it? Atmospheres. Okay, the number's right. It's atmospheres. Liter's not a unit of pressure. There we go. Good grief. Any questions? Am I done? No. You got a question?
Yeah. R is the same in all these equations?
R is the same in all the equations. It's constant. Yeah, if we're using these units. There are other expressions of it, which is just like you can take a piece of paper that's 12 inches long, and you can say that's 12 inches long, and somebody else can say, no, that's 1 foot long. You're both correct, right? So if we use different units on this constant, the number's different, and we'll encounter that later this semester, 8.314 liter atmosphere. Joules per mole Kelvin, sorry. Joules per mole Kelvin. But it's a constant. So this also asks for the pressure in PSI. So then we need to do a conversion here. To do my conversion, I'm going to use the unrounded value that I had, 1.6253 atmospheres To convert to PSI, I can do this in one step. I go to the table and it says 14.7 PSI is equal to 1 atmosphere. I have that memorized. I don't expect you to remember that. So then I'm going to get 23.892 PSI. Rounding that, I get 23.9 PSI. Any questions? Here's another one. What volume does 0.556 moles of gas occupy at a pressure of 715 millimeters of mercury and a temperature of 58 degrees Celsius? We could make a table, but now we're kind of awake and we recognize there's nothing changing here. I've got one measure for moles, one number for pressure, one number for temperature. I don't actually need a table. I could just write this down. So I've got 0.556 moles, and I say, well, what variable represents that? Well, that's N for number of moles. And then I've got 715 millimeters of mercury, and it says pressure of, so that's the pressure, and then a temperature of 58 degrees Celsius. I am trying to find the volume. What volume? So I take PV equals nRT, and I'm going to divide both sides by P. So the P's cancel out. And just to save some time, I'm just going to erase them. And then I can put my numbers in. N is 0.556 moles. R is 0.08206 liter atmospheres over mole kelvins. And then I get to my temperature. Can I put 58 degrees Celsius in there? No. Gas law problems, you have to use Kelvin. So I need to convert that to Kelvin, and it's easiest to do that before I stick it in there. This is to the nearest 1 degree, and so what your book often does is they just use this conversion factor to the nearest 1 degree. It's a little bit sloppy, but I could see the point there. You can do 0.15 if you wish. I'll do, since I wrote it, I'm going to do the 0.15 today. It usually doesn't make much difference. 58 plus 273.15. My Kelvin temperature is 331.15 Kelvin. In terms of significant figures, the uncertain digit in 58 degrees Celsius was in the ones place. In my converted temperature, the uncertain digit is in the same place. The difference here is just a matter of adding, and so we've actually gained a significant figure here. That can happen. So 331.15 Kelvin. And then I'm going to divide by the pressure. And yeah.
So I know this is kind of a question, but when we're adding, when it comes to significant digits, we're going to be using the one with the most?
That's a good question. So what about sig figs and adding? So the rule is the fewest number of decimal places. So this actually had no decimal places, right? This number has 2 decimal places. So this one has fewer decimal places, so the uncertainty is going to stay here. Another way to think about this, So 58 degrees Celsius, the uncertainty there is plus or minus 1, right? And when we look at 273.15, the uncertainty is plus or minus 0.01, right? When we add these two together, the uncertainty in our final answer is the larger of these, because you can't become more precise just by adding a number to it. So that means my answer is going to be plus or minus 1. And so that's why I've underlined the ones place. These digits might or might not be important in terms of rounding errors or something, but the uncertainty is here in the ones place. Does that make sense?
Yeah.
That was an excellent question. Okay, so can I stick this 715 millimeters of mercury in the denominator? No, I can't. Because look what's going on with the units here. Moles cancel. That's great. Kelvins cancel. That's great. But I've got liters and atmospheres. Millimeters of mercury is not going to cancel with that. So I need to convert this. So I need atmospheres, and I'm going to divide by millimeters of mercury. So the units work out. Pressure conversions can always be done in one step. So 1 atmosphere is how many millimeters of mercury? 760. That is an exact conversion, an exact relationship. So 715 divided by 760. 0.94078 atmospheres. This number is a whole number, but it's not an exact number. This has 3 sig figs, and so my answer has 3 significant figures. To avoid rounding errors, I'm just going to carry 2 extra digits. Remember, 1 atmosphere is like normal pressure, right? So 0.94 atmospheres is just a little bit below normal pressure. If you get into something like 5,000 atmospheres, that's a very unusual situation. So now my atmospheres cancel out. So I've got 0.556 times 0.08206 times 331.15 divided by 0.94078. And this is equal to 16.059. 3 significant figures is the smallest number of sig figs in any of those. And so this is, the unit left is liters. The nice thing about carrying 2 extra digits here, that the next digit is a 9. If you keep 2 digits, you don't have to worry about rounding those at all. That'll take care of itself. So then I can round this to the 10th place, and I'm going to come up with 16.1 liters as the volume. Any questions?